לא, בסדר, אבל לא יורידו לך מתחת לזה.
מתחת לזה אתה מאבד את הזכויות שלך לדברים שלך. אז הדוקטורנט כאילו שאתה מקבל, אז מינימום זה 7. אז לכן, תכף נשים את זהו, שם הם שמו את הרף, זהו.
כן, טוב. התחיל להקליט.
מפתיע אותי שנתן לא פה. מפתיע אותי שנתן לא פה.
Hi everyone, it's a great pleasure to start again this seminar series. Our first speaker will need no introduction, our very own Orit.
Okay, thank you. Let me just close the lights. I think this is better. Yes, so thank you. I'm very happy to give these talks. I'm going to give a talk today and then another talk on the 17th. And I've had a prolific sabbatical, more or less. I managed to publish four papers as first author. So I'm going to talk about 2 today and another 2 on the 17th. When I said prolific, not as prolific as Chaim, that's like an off year for Chaim, but for me that's a prolific year. And so this was done more or less during my sabbatical, and the 2 papers, one of them, the first one is about this notion of tropical modality. Is really the hardest paper I've ever managed to publish. I really had to fight with the reviewers to even convince them that I actually have something to say. And the second one is like the easiest, the smoothest submission I've ever had. It was like really minor comments, really great work, just publish. I was there's this disparity between my expectation and how hard or easy it was really to publish. And I've noticed another interesting aspect of the 4 papers that I'm going to talk about, that all of them began as undergraduate projects. Some with Maya Shulki and another student who is not here, Noam Cohen. And there's probably a lesson to be learned here about the benefit of having a project with undergrads. I'm not quite sure what it is, but it is interesting. Okay, so let me just read the title. So it's Tropical Modality and the Influence of Equatorial Cooling on the Large-Scale Circulation. So I'm gonna try to explain what I mean by tropical modality, and then show how equatorial cooling, the fact that we have equatorial cooling in the climate system that is related to the coupled ocean-atmosphere circulation, how that has a fundamental effect on the large-scale circulation. So beginning with the very, very basics, so our very basic understanding of the large-scale circulation on Earth is it goes back to the notion of a Hadley circulation, which I'm pretty sure everybody here is familiar with that idea. So the idea is that you have a rising branch in the equatorial region, and when the air rises, it precipitates and so forth. So under really idealized conditions, and this is actually taken from an aquaplanet simulation, meaning a coupled simulation where you have no continents. This is what you would expect to see. You would expect to see a tropical rain belt, so this blue thing here is precipitation, which goes along with the rising branch of the Halley circulation, and then a descending branch where you have no precipitation in the subtropics and so forth. So this is what you would expect under idealized conditions. However, when we look at observations, we see a very different picture. When you add continents, when you break this symmetry of an aquaplanet, what you get is a complex distribution of precipitation. And a lot of what I've been doing in recent years is trying to understand this distribution of precipitation, how it changes seasonally, and so forth, the role of continents and other aspects as well. So this is how precipitation looks in the present climate. And as you can see, In some parts, so this is what we call the ITCZ, the Intertropical Convergence Zone. This part in the Pacific is what we associate with the rising branch of the Halley circulation, but we also have precipitation south of the equator as well. And the Hadley circulation paradigm does not account for having more than one ITCZ, one on either side of the equator. And this we call the SPCZ, the South Pacific Convergence Zone, for which there is actually no good theory. And also, during boreal spring, so this is now the annual mean northern hemispheric summer, southern hemispheric summer. So around boreal spring, we get a double ITCZ, an ITCZ on either side of the equator in the eastern Pacific as well. And this doesn't go along well with this idea of a Hadley circulation, because with the Hadley circulation you would expect a single ITCZ. So that's something we want to understand better. And if we examine at least simulations of past climates, so these are simulations done by the HAD-CM3 model, where the only thing that is being changed is the geomorphology, right? So we're tracing back how continents looked like billions of years ago, and we're fixing CO2 levels. So the only thing that changes is the geomorphology. And as you can see, the precipitation distribution changes a lot, and in some climates, you actually have a really, really pronounced double ITCZ. So this is clearly not a Hadley circulation. It's something else. What I'll try to show you in this talk is we can refer to these as not really a Hadley circulation type climate, but rather an anti-Hadley circulation type climate, where you have rising branches on either side of the equator and a descending branch at the equator, so it's actually the reverse of a Hadley circulation. But this changes a lot from climate to climate, and if we look at the zonal mean precipitation, in some climates we have something that looks more like a Hadley, where like a dominant peak, but in some climates we really have two dominant peaks. So is this important? Should we distinguish between climates where you have this double ITCZ, pronounced double ITCZ, or a single ITCZ? So that's the idea of tropical modality. The paper that got me interested in this is this paper by Armstrong et al. This is again from the same set of simulations of the HAD-CM3 model. And I was reading this paper, and I noticed something weird, which is the ITCZ, the Intertropical Convergence Zone, would tend to follow the sun. It follows the sun in its seasonal cycle. But in this paper, the summer ITCZ in the northern hemisphere was closer to the equator than the winter ITCZ. So it's counter to the very basic intuition that we have about the ITCZ. So like either this model is wrong or this is very interesting. So I actually emailed Armstrong, and this is how I got in touch with the people who actually ran these simulations and got this whole project running. So this is interesting. This shouldn't happen. The ITCZ should follow the sun. So how come it doesn't? So that's another interesting aspect of what happens when you have a double ITCZ. Another reason to study climates where you have more than one ITCZ is the very well-known or rather notorious double ITCZ bias, where climate models tend to have, so the black contours here are the observed precipitation, and the blue colors are the ensemble mean of CIMIP 5 models. And climate models tend to simulate an excess of precipitation south of the equator in the Pacific. So they have a climate that looks more like a double ITCZ than a single ITCZ. This is a very common feature of climates, of climate models, and it's not really well understood why this happens, but it's a very common feature. So we would want to understand why this happens. And if we look at the double ITCZ bias across CIMIP generations, so CIMIP 3, CIMIP 5, CIMIP 6, it really hasn't changed. Everything about these models, more or less, including resolution and so forth, had changed, but this bias has remained essentially the same. So it really suggests that there's like missing physics in climate models that we just haven't found out. You know, what is this missing physics? But there's clearly missing physics that is very fundamental, because it's not dependent on the parametrization scheme or resolution or anything like that. So it would be interesting to understand what generates a double ITCZ. And this also affects the projections. So this is the projections of the change in precipitation in simplified models under quadrupling of CO2 concentrations, and there's clearly a strong double ITCZ signal, so it's not really well known whether this is due to how is this affected by the bias that the models have. So it's important also for understanding how climate might change. And finally, this double ITCZ bias is known to be related. It's not just an atmospheric bias. It's known to be a coupled. It's a feature of coupled climate models, and it has its counterpart in the ocean component. So a very well-known bias in climate models is the cold tongue bias in climate models. So climate models tend to have, so shown here is SST, and this is the ensemble mean bias. So climate models tend to have a cold tongue bias, where the cold tongue in the Pacific and Atlantic is too cold and too westward extended. And in a recent paper with a student called Meyer Samuels, we show that climate models also have a shallow thermocline bias in the southern hemisphere, where the thermocline is way too shallow in the subtropical Pacific, southern subtropical Pacific, and this is closely related to the double ITCZ bias as well. Not clear whether this is driving the bias or is affected by it, but it's definitely related. So all of these make it interesting to or motivate this notion that I'm going to try to convince you is an important parameter called tropical modality. Okay? And later on, I'll try and link that to equatorial cooling and maybe biases in equatorial cooling as well. Okay, so the basic question we started the project with is, can we objectively quantify the modality of the tropical rainbow? Meaning, here I have a precipitation distribution that, at least in the zone mean, leads to, in observations, a dominant single peak. But then, if you look at for example, pre-industrial conditions of this climate model, the HALCM3 model, we have an almost symmetric precipitation distribution. And then if you go back to some past climate where you have a pronounced double ITCZ, you have these very strong peaks on either side. Is this important? Does this affect the climate? Does this affect the seasonal cycle of the ITCZ and so forth? And if so, how can we distinguish between these different climates? Can we quantify, when I say modality, what I mean is, in a distribution, a mode is the maximum of that mode. So this would be close to be a unimodal distribution. And when you have double peaks, that's a bimodal distribution. So that's where the word modality comes from. So can we quantify the modality of the distribution? How close are we to a unimodal precipitation distribution, which is what you would expect under a Hadley circulation conditions, versus a bimodal distribution, which is what you would expect for a double ITCZ dominated climate? So that's like the first question. Can we objectively quantify the modality? And I'm going to call this parameter that I'm going to define tropical modality. How close are we to a unimodal versus bimodal distribution? And then once we quantify this, how does this parameter, the tropical modality, affect the large scale circulation and also the seasonal cycle of the tropical rainbow? Do climates that are unimodal or bimodal look different? And the intuition is that yes, of course, if the Hadley circulation determines a lot of the properties of the climate that we see today, if we have a different type of circulation, an anti-Hadley circulation, it should affect the large-scale circulation and other climate parameters as well. So the way I went about this is okay, so shown here in the left column is the observed precipitation, and the thin colors are seasons, but let's not talk about that for now. And then I decompose this into a hemispherically symmetric component and a hemispherically anti-symmetric component. So you can take any distribution and decompose it into a hemispherically symmetric component, which is shown here in the center, and a hemispherically anti-symmetric component. And what you can see is that the hemispherically anti-symmetric component doesn't really contribute much. There's a very strong hemispherically symmetric component, and really the modality is really just related to the hemispherically symmetric component. And it's quite clear that it has something to do with the extent to which precipitation is inhibited at the equator. the more precipitation is inhibited at the equator, the more significant is this bimodal distribution. If there's no inhibition at the equator, you would get a unimodal single ITCZ, and if there's strong inhibition, you get a very pronounced bimodal distribution. So equatorial precipitation seems to be a very key thing here. And the parameter I've defined, and I've argued about this with the editors of this paper a lot, the parameter is just one way of quantifying it. I'm going to argue that this notion of tropical modality is a much general thing. It's not dependent on the parameter. You can define it in many ways, but I found this to be a very useful parameter of modality, and I call it the equatorial modality index. And it's very simple, just 2 minus some parameter alpha, which is equal to 0.45, but that's not really critical. And really the key thing is that if you normalize precipitation between 0 and 1, then you just take the precipitation at the equator and divide it by the mean precipitation in the tropics. Okay? And there's this additional component here which accounts for the fact that even if you have a unimodal distribution, but that is shifted off the equator, you would still have precipitation at the equator that is not equal to 1 if it's normalized. So if you assume this is a Gaussian, this part accounts for that. Okay? But in essence, it's basically the ratio of equatorial precipitation to mean precipitation. And this gives you a parameter that is between 1 and 2. So 1 would be a unimodal distribution, and 2 would be a bimodal distribution. Okay? Again, it's one way of quantifying it, but it gives me an intuitive number that tells me, am I close to a unimodal type climate or a bimodal type climate? 1 and 2. And if you take this set of simulations that I showed before with the HALCM3 model, when you change the geomorphology, this parameter, if you take like a composite of low EMI versus high EMI, it captures very well the unimodal type climates versus the bimodal type climates. So it does this job of distinguishing between climates that have a bimodal distribution and a unimodal distribution. And similarly, if you take 73, 5, and 6 models, and you try to distinguish between, you do a composite of high EMI versus low EMI, it really nicely captures those models that have a strong double ITC bias versus models that don't have a strong double ITC bias. So it's a useful parameter in that sense. It does what it's supposed to do, distinguish between different climates. And if you go back to this set of simulations where you change the geomorphology, then we see, so these simulations have a fixed CO2, and the only thing you change is geomorphology. And you see that if you go back along the historical record of the past 300 million years, again, just driven by changes in geomorphology, this EMI changes from climates where you have 1 to climates where you have 2. So during the Cretaceous, it shifts from 2 to 1, which is a period of strong warming. So there's definitely it goes along with known climatic variations. The change in global mean temperature is very small, but there is some dependence. It's very small, however, but this is mostly because it's fixed CO2. Okay? So it doesn't mean that it doesn't change with global mean temperature, just this experiment doesn't capture it. But an interesting feature of this set of experiments is that equatorial, so that the tropics to pole temperature difference varies very strongly with this modality. Okay, so this equatorial modality index, or the modality of the large-scale circulation, is strongly related to changes in the temperature, in the tropics to poles temperature difference. So that's one thing that comes out.
Can you just help us? What's the difference between the Jurassic and the Cretaceous era? What was the characteristics of the climate?
This, correct me if I'm mistaken, but this was a very warm period. And then this cooled, and then this warmed again, right? So the late, I hope I'm not confusing you, but the late Cretaceous. Okay, sorry. So is this a cooling period? So the late Cretaceous is known to be the warmest period. Any paleo people here? So 60 million years was the peak in temperature, but I also remember that during the Jurassic there was a warm period as well. So I think this is a period of. I hope I'm not getting this wrong, but either cooling or warming along this
Anyway, you don't capture it, right? It doesn't matter.
I'm sorry?
For this set of simulation, it doesn't really matter. Because
No,
you don't
here,
capture
no, it doesn't capture the changes in global mean temperature, but interestingly, this is seen in the observational record. A strong change in equator to pole temperature difference is seen in this period as well.
This is from the model, it's not from...
No, this is from the model, but in observations, you see a very strong, during the Cretaceous, we published another paper in Nature Communication with Kamshal that tries to explain, using this set of simulations, how geomorphology is really one of the ways to explain how temperature, the tropics to pole temperature difference varies a lot during the Cretaceous. So it definitely has something to do with the geomorphology. But you're right, I just don't remember. It's either strong cooling or strong warming here. That goes along with a strong change in equator to pole temperature difference.
Isn't it related to the opening of the Atlantic Ocean?
It's more complicated than just that, because there are complex changes in the basins. What we show in that paper is that the changes in the dimensions of the basins affect the efficiency of ocean heat transport, which then changes the equator to pole temperature difference, but it's way more complex than that.
I have a general question. So when you go back to your earlier periods, do we know what the topography was like? And is the topography also time varying, or just the orientation of the continent?
This is not continuous. This is that slices.
Yeah.
But yeah, this is estimates to the best of our estimates of geomorphological states going back 300 million years.
Does that include topography or just
It's the ocean. It's the bathymetry and topography.
topography also? Okay.
Yeah. So it's the whole thing.
Yes, so how much of it is continent, like where the continents are versus how much versus mountains. Like there's the stationary areas in the atmosphere would be very different depending on where the topography is and whether the topography has a big influence or not.
So I think it accounts for both topography and bathymetry. So both. So I guess your point is that it shouldn't be just the ocean. It's also the topography that affects the circulation. That's also a component that definitely affects the climate change as well. And we actually haven't looked at that part in this work. So another interesting aspect of this EMI is that even though it's defined at the equator, it's strongly correlated with changes even in much higher latitudes. This is a correlation of 1, -1, and we're reaching almost 1 even in the exotropics. This is for CMIP-5 models and for the HAD-CM3 model. So this index, because it's essentially related to the large-scale circulation, is strongly correlated with precipitation minus evaporation here, which is a very good index for vertical wind. But also, if you just take parameters of the large-scale circulation, so it's strongly correlated with the tropics to pole temperature difference, equatorial net energy input, the Colton index, how much the Colton is cold or not, the width of the radianal overturning circulation, the intensity of the radianal overturning circulation, the intensity of the Walker circulation or the dominant zonal overturning circulation in each climate, and with the width of the IPCZ. So without going into specific data for each of these parameters, the point I'm trying to make is that this is a very informative parameter. Knowing the modality of the climate tells you a lot about that climate, not just something that has to do with precipitation distribution. And the second question was, how does this EMI, or the modality of the climate, how does that affect the seasonal cycle of the ITCZ? So this is taken from observations. So in the Atlantic, we have a single ITCZ in the present climate. And really, the EMI of the Atlantic is 1. So that's consistent. And we just have this seasonal variation of the ITCZ going north and south following the sun. And this is what you would expect for a Hadley-like monsoonal type seasonal variation. However, in the Western Pacific, we have the SPCZ and ITCZ. We have 2 ITCZs. EMI there is 1.7. And as we can see, there are additional modes of variability. We have an ITCZ that changes seasonally north of the equator, and another one that changes seasonally south of the equator. So we want to define these added degrees of freedom, or added modes of variability. And the 3 dominant ones that at least I found for a bimodal climate are that the shift of precipitation distribution, the precipitation distribution shifts basically towards the warming hemisphere. So you see that, but not in the sense of a monsoonal circulation. It just shifts a little bit, and it does that for each of the IPCZs. So the red line here is just a centroid. So if this was a unimodal climate, it would follow this centroid of precipitation. But as you can see, there's basically no precipitation between these two ITCZs. So it's just this, the precipitation distribution generally shifts towards the sun, but not in the classical or Hadley-like way. So that's one mode. There's the second mode is variation in the separation between the hemispheric rain bands. So the distance between the hemispheric rain bands, that changes seasonally as well. So that's another independent degree of freedom. And then there's this seesaw variation that was previously observed by Zhao and Fedorov of the hemispheric rain bands. So it's just the intensity. So in some climates you would have no shift at all of the ITCs, and the only thing that changes is just the amplitude of the ITCs. So that's what they call the seesaw mode. So these three modes describe the seasonal variation of the ITCZ in a bimodal climate. And an interesting feature of a bimodal climate is, as you can see here, so in high modality climates, the hemispheric ITCZs do not always follow the sun. So here you see this centroid follows the sun, but for example, the southern hemisphere ITCZ can shift counter to the sun. So this explains this observation that I saw with the paper by Armstrong, that for a bimodal climate, ITCZs or hemispheric ITCZs do not necessarily follow the sun. And that's important when we try to interpret paleo proxies. We should not always assume that the precipitation follows the sun. We should first distinguish between bimodal and unimodal type climates. So just to summarize this part, so I'm claiming the tropical...
When you said not follow the sun, you mean in terms of precipitation or also in terms of temperature?
Usually precipitation goes along with temperature. So if you have an IPCC here, usually that would go along with the temperature peak as well. So that would probably go along as well with the peak in temperature that lies beneath that tropical rain belt. So just to summarize this part, so tropical modality I'm claiming is an important climate characteristic that summarizes our ignorance of variations in the tropical rain belt. I'm suggesting EMI as an objective way of quantifying tropical modality, but again, I think the concept is independent of the actual parameter I'm using. And low tropical modality climates are Hadley-like, but high tropical modality climates are characterized by sort of these additional modes of variability, and also they are wider and weaker. The circulation is wider and weaker. There's a weaker tropics to pole temperature gradient, and there's these, instead of one, there are these three modes of seasonal variation, which are, as I've defined before, the migration, separation, and seesaw. And then hemispheric ITCs do not always follow the sun. So I'm a bit, I think, stressed for time, so I'm just going to move on to the second part. And really what I've been talking about is basically distinguishing between this picture and this picture, right? So a unimodal, or EMI equals to 1, is the classical Hadley circulation. And a bimodal distribution, or EMI equals 2, is an anti-Hadley circulation. And what causes the large-scale circulation to shift from a Hadley-like to an anti-Hadley circulation is equatorial cooling. Equatorial cooling comes about because of the coupled nature of the atmosphere and ocean. And essentially you have circulation in the ocean. These are, in the Pacific, these would be called the subtropical cells, that causes upwelling of cold waters along the equator. And if this cooling is strong enough such that there's an energy deficit in the equator, such that the circulation needs to actually overturn to now transport energy towards the equator, because the ocean is sucking energy from the atmosphere so efficiently that now the atmosphere needs to compensate and transport energy back to the equator, then the circulation would reverse and you would get an anti-Hadley circulation. So the coupling to the ocean and the extent or the intensity of equatorial cooling is very critical for this transition from a Hadley to an anti-Hadley circulation. And very likely the variation between 1 and 2 goes along with the extent to which this coupling occurs. I mean, how much the strength of this coupling, and how much of a cold equatorial time exists that creates this variations in modality. Okay, and so this is how the surface energy budget looks like in the present climate. And as you can see, again, this cooling comes from the equatorial cold tongues in the Pacific, Atlantic, and to some degree in the Western Indian Ocean. And changes in the intensity of these equatorial cold tongues, specifically in the Pacific, is what we call ENSO, right? El Nino and La Nina phases are warmer than usual and colder than usual cold tongues, essentially. You can think about it in this way. And they also have a very strong zonal mean component. So when there's an El Nino event, there's relatively strong zonal mean equatorial warming versus La Nina events where you have zonal mean cooling along the equator. So this variability introduces changes in the mean net equatorial cooling, which could affect the large-scale circulation. And the very well-known relation of ENSO to the large-scale circulation, first shown by Seeger, or maybe publicized by Seeger, and this is sort of this remains today an open problem, how ENSO is related to the large-scale circulation, and there is no paper that I know of that really explains this very well. So shown here are the differences between Nino and Nina states. So this is the shaded, or the pale lines are the stream function, and the colors are the change in the stream function. So during Nino conditions, the circulation strengthens and narrows. The Hadley circulation strengthens and narrows. And similarly, during Nino minus Nina states, the subtropical jets strengthen and shift towards the equator. This is not an intuitive change, because if we think about the subtropical jets as being driven by conservation of angular momentum, then a shift toward the equator should not go along with the weakening of the jet, with the strengthening of the jet. It should actually go along with the weakening of the jet if it's just about conservation of angular momentum. So this is not an intuitive change in the strength of the subtropical jets. But this is very well known, and as I said, there's no explanation for this, I think, so far. Another interesting thing is that in observations, we see something that looks like an equatorial cooling over the past few decades. However, basically all climate models predict with global warming equatorial warming as well. This is a very well-known paradox, and it's clear that if the models produce a bias in the amount of equatorial cooling, that probably affects the large-scale circulation in some way that is not still well understood. But this bias, this is from a paper by Seeger, a Nature paper by Seeger et al., really makes a very good point that even though we don't quite understand why, it's very clear that there's a bias in the trend. In observations, the equatorial regions are cooling versus climate models where it's warming. So it's important to understand how this affects the large-scale circulation. And what I first did is I ran, an aquaplanet simulation where, so you don't have any continents, and this is actually an idealized coupled model, so there's some representation of the model, of the ocean, and what I control for here is the stratification of the ocean, and what this does is I can control for the intensity of the cold tongue. If the ocean is more strongly stratified, you get a stronger cold tongue. And so I'll just go over this very quickly. So this is just the energy balance at the top of the atmosphere and at the surface. And as you can see, I'm cooling more and more at the surface. And as I increase the cooling, you can see that the SST at the equator becomes more cooler and cooler, but also the equator to pole temperature difference also decreases with increasing, with intensifying equatorial cold tongue. And as you can see here, so this is the zero line, right? And this is vertical wind. So as the intensity of the cold tongue increases, at some point the values here become negative. And when you have a vertical wind that is negative at the equator, this means you have a descending wedge or an anti-Hadley circulation. So as I cool further and further the cold tongue, I get an anti-Hadley circulation. And this is the upper level zonal mean wind. So we get a poleward shift of the subtropical jet as we increase equatorial cooling, which is consistent with the response to La Nina conditions. No, I'm sorry. This is the meridional wind. So this would be a weakening of the Halley circulation, and this is the subtropical jet, so we see a forward and weakening of the subtropical jet, okay, consistent with La Nina conditions. And these are the surface winds where the latitude between easterlies and westerlies shifts forward. So this is again consistent with a shift of the poleward extent of the Halley circulation. So we can capture this sensitivity in an idealized aquaplanet model. And so if we can do it in these idealized conditions, the next step would be to ask, can we study this system when in addition we also remove a zonal asymmetry? So a very classic model of the atmosphere, a classic approach to understanding atmospheric dynamics is to first look at axisymmetric models. So axisymmetric models are models where the circulation is symmetric about the circulation axis of Earth, the axis of rotation of Earth. Okay? And a very, perhaps even the most fundamental theory of atmospheric circulation is called the Held-and-Howe model, where, again, you assume axisymmetric conditions, so you have no eddies, and you try to relax the atmosphere to something that mimics the distribution of the differential warming by the sun. And what you get is, you get these two regions of the atmosphere. One is where you have a circulation cell, or the Halley circulation, where angular momentum is conserved, and you get a subtropical jet due to conservation of angular momentum as the air moves poleward. And you have within the circulation cell, so here this line here would be the height profile or the temperature profile, and the dotted line is the profile to which you're relaxing the atmosphere. So when this is higher, so this shaded region is where you have warming, and this shaded region would be analogous to the subtropical regions. So this is where you have cooling, and these need to equal each other, so you have net. So this is energetically closed, and outside the tropics, outside the circulation cell, you just have relative convective equilibrium. Okay, so this is the very simple axisymmetric model that you study in each introductory course to atmospheric dynamics. And really the exercise that I wanted to do is what happens when you add equatorial cooling. Just concentrated equatorial cooling, how does that affect this very simple, very well-known axisymmetric model? So that is just an exercise. So it began sort of as an exercise. And to put this in context, a similar work was actually done by Howe and Lindzen many years ago, but they looked at the effect of concentrated heating. And the idea here was that the ITCZ, or along the ITCZ, you have very strong warm or latent heating because of the release of latent heat. So they thought of the ITCZ as being a heat source, and how that might affect the atmosphere. But I'm claiming that this is actually not, and their finding is that this concentrated heating does affect significantly the circulation, so it's an important thing to look at. But my claim is that equatorial cooling is a way more important driver of the changes in AOC, and I just wanted to isolate that and look at that. And as you will see, the results are fundamentally different because with strong equatorial cooling, you can actually bifurcate the circulation from a Hadley to an anti-Hadley circulation, which is fundamentally different than what would happen for just concentrated heating. Okay, so I'm not going to go into the equations. I'm just going to present the model. I'm not going to do anything mathematical here, but I'm just going to show you the model. So it's a 1.5 layer shallow water model. So these would be the momentum equations, and this term here is mixing. So in the rising branch of the circulation, you just let the surface winds and upper winds sort of mix, so they sort of damp each other. So that's this term. You have a continuity equation, and the whole model is just forced by this relaxation, this source here, a relaxation towards some height profile, which is sort of known, right? It's the height profile you would assume to have under, say, for example, a radiative equilibrium. And what I added to this very well-known distribution is just a cooling source. It's just a sink of heat, which is just basically a Gaussian. So I added this Gaussian heat sink into this. Really looks like this, right? So it's just this Gaussian heat sink. And a very minor novelty of this model is that the surface winds can actually be diagnostically set by knowing the upper level winds, which is something for some reason no one had done before, but I can diagnostically calculate the surface winds as well. And really, this is very well known. So the way you solve this model is you assume that this is an energetically closed circulation. You assume angular momentum conservation in the circulation cell and then relative equilibrium in the exotropics, as I showed before. And you assume that the angular momentum of the upper branch, which this is what angular momentum is given by. So you assume that it's determined by the latitude of the rising branch. So the air rising here and reaching the upper branch, that the angular momentum at the surface actually determines the value of the angular momentum in the upper levels. And in this latitude, the zonal mean wind equals 0. So you actually know what is the angular momentum of the rising of the upper branch by knowing the latitude at which the rising branch occurs, because u is equal to 0. So it's actually just this thing. And an important thing to notice is that the more poleward the rising branch is, the lower the angular momentum of the upper level. And then the two new things about this solution are that I assume that the standard deviation of this Gaussian sink is sufficiently small such that when you integrate, you just get the amplitude of the integral of the integral. So it's just a number. And for the solutions, I neglect vertical advection of momentum, this link with the surface, just so these equations can be solved. And after some algebra, you basically get this term. It's not a nice looking term, but you just need to find the roots of this term. So mu j would be the extent of the circulation, mu I would be the latitude of the rising branch, and h1 is the equator to pole temperature difference, and RT is a very known parameter called the thermal Rossby number. So I'm not going to go into that, and it's written in terms of, instead of phi, in terms of mu, which is the sign of phi. So it really just boils down to finding the roots of this complicated algebraic expression. And this is how a solution would look like when you have equatorial cooling that leads to an anti-Halley circulation. So again, mu j is the edge of the circulation, mu bar is the latitude where you go from heating to cooling, which would go along with the latitude of maximal circulation, and mu I is the latitude separating the circulation cells. So here, this is the meridional wind. Here it's negative and here it's positive. That means you have an anti-Halley circulation. You have flow towards the equator from this point towards the equator, and flow away from the equator poleward of this. So it's an anti-Halley circulation. And this is how the surface winds would look like. And you can so one interesting thing about this model that, yes, you can generate these anti-Halley circulations, but you can also predict the critical cooling at which these anti-Halley cells emerge. And an interesting feature about this critical amplitude is that it's very strongly dependent on the equator to pole temperature difference. So this is consistent with what I showed before about modality, so that there's a very strong link between modality and the equator to pole temperature difference. So it's consistent. So that's nice. That's one nice aspect of this theory, and it predicts a higher prevalence of high of high modality climates in climates where you have a weak equator to pole temperature difference, which is again consistent with the simulations I showed. Because I'm running out of time, I'm not gonna describe this, but there's another interesting aspect of the solutions, and this is just to show that, well, the numerical solutions are very consistent with the analytical solutions, and the prediction for the critical amplitude at which an anti-Halley circulation emerges is very well predicted as well. So the analytical solutions approximate very well the numerical solutions. I'm going to jump over this. And then really what I want to talk about is, can these solutions explain the relation of ENSO and the MOC? So I want to propose a mechanism for explaining how equatorial cooling explains, or how this model explains the relation between ENSO and the MOC that I showed before. And the mechanism goes as follows. When you have equatorial cooling, this would force a poleward expansion of the rising branch of the Halley circulation. So, for example, if we add this cooling here, then we've taken away, area of warming from this region, and here, this area now has more cooling, so the boundary between these two regions needs to shift forward, so that the net area of cooling versus warming is again 0. So when we add equatorial cooling, this boundary needs to shift forward, and this is indeed what happens. Okay? So the rising branch expands. Okay? If the rising branch expands, then rising air from the surface now draws angular momentum from higher latitudes, which have a lower angular momentum at the surface. So as equatorial cooling leads to an expansion of the rising branch, and this in turn leads to a decrease in angular momentum, as you see here. So this makes sense. So you're decreasing angular momentum, and you're expanding the rising branch. And then, if you add again the constraints of continuity and energy conservation, this for a steady state solution to exist, you also get this forward expansion of the Hadley cell, and actually a decrease of tropical height. This in effect reduces the equator to pole temperature difference and also the gradient of height or temperature in mid latitudes. What this does is the following. So as I said, if you add equatorial, so now I'm gonna reverse the argument so that it would match the observations which I'm showing in terms of Nino minus Nino. So what I've just said, I'm just going to say in reverse for warming. So as you warm the equator, you would get an increase of angular momentum, and therefore an increase in the amplitude of the subtropical jet. But what you also get is a contraction of the Hadley cell, and the subtropical jets go along with the edges of the Hadley cell. So this explains why the Hadley cell contracts and why the subtropical jets actually strengthen, because you increase angular momentum. Okay, so this is consistent with that. And similarly, what I just said before, you get a strengthening and contraction of the Hadley cell. Okay, so this mechanism is consistent with what happens during ENSO events, so it does explain. And the question is, how much does this mechanism account for really these changes, or is it really eddy variations? And what I'm going to claim is that the changes in temperature gradients and actually jet intensity affect the baroclinicity and just reinforce this mechanism. So what I'm claiming is that this is a mechanism for the changes that we see, and the eddy response is actually a reinforcing response to the axisymmetric response, but not a driver of the response. So this mechanism does indeed provide an explanation for how ENSO affects the meridional overdynamic circulation. And again, the eddy response is just a reinforcing response. And this is to be determined, so work that is now being done by Noah and Cohen is trying to really look into observations and see whether we're right and whether really the eddy response is a reinforcement of the axisymmetric response, and in which case, yes, this mechanism explains the relation of ENSO and the MOC. So just to conclude, axisymmetric theory provides a simple framework for understanding the transitions from Hadley to anti-Hadley circulation, and it does capture the observed response to equatorial cooling. We think we provide a mechanism for explaining the relation of ENSO and the MOC, which has been an open question for the past 20 years. And it also provides insight on the implications of the equatorial warming that we see in response to global warming. So for example, one of the implications would be that the widening of the Hadley circulation in a warming climate in climate models is biased. So climate models do not widen fast enough in climate models, which would affect, for example, desertification. And as I said, there's ongoing work really to test the validity of this mechanism. Thank you for listening. I'm sorry for sort of rushing through the last part because we're out of time. And yeah, thank you.
Yes, I guess what the last part was really interesting. So I'm trying to, there's long-standing like confusion about global warming versus El Nino in terms of equator shift versus polar shift of the jet. And yeah, so here you're capturing the equator shift of the jet. I'm wondering if global warming, so if global warming, that doesn't happen. So I'm wondering if there's something special about, I mean, I don't think that's why, but like, I'm wondering if this particular conceptual model can be
I think